Okay, over the last couple of days in class, we've been looking at the qualitative analysis for adding energy or removing energy from a system as we have things go through phase changes. So we did our energy bar graphs to represent the change in thermal energy as things get warmer and colder, and then the change in interaction energy as things go from solids to liquids, liquids to gases, and vice versa. What we're going to get into now over the next few class periods is the quantitative nature of how much energy is being added or removed from the system. And so that means we got to talk about something called heat capacity, as well as heat of fusion and heat of vaporization. So, before we get into that, remember when we talk about heating, heating is the process of energy being added or removed from a system by the collision of particles. And like we did in our energy bar graphs or LOL diagrams, heating is represented by the letter Q. So in our calculation stuff here, you're going to see the letter Q, and again, that represents the energy being added or removed from the system. So talking about the transfer of energy, we've already reasoned that heat depends upon not just the amount of kinetic energy, but also the mass of particles. So we're talking about thermal energy, we're talking about the total quantity of energy, so how many particles are present also have an effect on how much energy has to be added to warm something up or how much energy has to be removed to cool something down. So any attempt to find out how much energy is being moved in or out of a system must take into account the object's mass. So mass and the temperature both play a role. We know that particle motion increases at higher temperatures and is lower at lower temperatures. Also, going back to the red and green demo from the previous unit, we saw that not everything changes their temperatures or heats equally. So we had the thermal expansion of water and alcohol. Alcohol responded to the addition of the heat much differently than the water. Well, same thing is going to be true here as we change the temperature of different substances. So there has to be some sort of inherent factor that determines how much energy is needed to change the temperature of a subject. Some things just warm up more quickly than others. So via experiment, it's been determined that it takes approximately 4.18 joules of energy. Joules is the unit for energy. It takes that much energy to change 1 gram of water by 1 degree Celsius. That factor is known as the heat capacity for water, the amount of energy it takes to change the temperature of 1 gram of substance by 1 degree Celsius. Okay, so with that heat capacity, we can calculate the energy that it takes to change the temperature of a substance by the following equation. Q, again, Q equals heat, so the energy transferred. Q equals the mass of the substance that we're working with times its heat capacity, so that factor that determines how much energy it takes to change the temperature by 1 degree Celsius, multiplied by the change in temperature. If we take that equation and we break it down into variables, Q equals M for mass times HC for heat capacity times delta T, or the change in temperature. The change in temperature is always calculated, always, and this is very important, final minus initial. Just like when we calculated the change in mass back in our very first experiment, final minus initial. It's always done that way. Okay. Now again, since we're dealing with the energy required to change the temperature of a substance, this is telling us how much thermal energy is added or removed from a sample of matter to raise its temperature or to lower its temperature. Okay. And we can tell the difference because if we're adding thermal energy, Q should be positive. And if we're taking energy out of a system, Q would be negative. So for water, the heat capacity of the liquid state is greater than the solid state. As we'll see here in a little bit when we get to some example questions, the liquid state has a heat capacity that's double that of the solid state, which means it takes less energy to change the temperature of ice than for liquid water, which should make sense because in the solid state, remember, those particles are very closely packed together. If one vibrates, it's going to vibrate all the ones next to it. Versus in water, where those particles are free to move, you can have a faster moving particle, but it's not going to directly impact the one next to it. It might have a glancing collision with it versus like a full head-on collision with those particles. So it's going to take more energy to make those other particles speed up. In general, solids especially with metals. Again, we're talking, this is applied to everything, not just water, but all substances. Solids have much lower heat capacities than liquids. Metals, like iron or copper, they have very low heat capacities, meaning that they very easily transfer energy and are considered good conductors of thermal energy. Now, what about during the phase change? We know that during the phase change, it also takes energy either being added to, say, melt an ice cube or boil water, or it takes energy to be removed to turn liquid water back into a solid. So does the same equation work for phase changes? And the answer to that is no, because during the phase changes, not only is there no change in temperature, so there's no change in temperature, that previous equation is not going to work. We're also not affecting the thermal energy of the sample of matter, we're affecting the interaction energy of the sample of matter. So for these phases, the constant that dictates the amount of energy absorbed is called either the heat of fusion, which is used for freezing or melting, so between solids and liquids, or the heat of vaporization, so the energy that's being added or removed when we are turning liquid into a gas or the gas turning back into a liquid. Like the heat capacity, these values are constants that depend upon the substance being considered. So all substances have different heat capacities. All different substances have different heat capacities depending on the state of matter, while all different substances also have different heat of fusions and heat of vaporizations, different amounts of energy to either melt or boil those substances. This heat is symbolized as HF or HV. As I've written it out here, we could say H fusion or H vaporization. But the equation overall is Q, again, energy being added or removed, equals mass, so how much of the substance still plays a role, and then whatever the heat of fusion or vaporization is for those substances. Those are constant values, just like the heat capacity. And we'll look at those values for water here in just a second. When we're talking about heat of fusion or heat of vaporization, that value for Q is looking at the interaction energy that's either being added or removed from the sample of matter. Now, in general, heat of fusion values are much smaller than those for heat of vaporization, which again we'll see in a second. It's much more difficult to rip particles apart, to let them go freely on their own. In other words, overcome all of the intermolecular forces between particles to allow them to go from the liquid into the gas state. That takes a lot more energy than it does just to add enough energy to get them to slip out of their orderly arrangement going from their solid to their liquid state. So, let's get into some practice with this. Okay, so we've got two different equations that we are going to be working with. We've got the equation for the heat capacity. So this is when we are just changing the temperature for a single state of matter. Or we have the heat of fusion or vaporization. So I'll put F or V, which deals with our phase changes. So just like we talked about with the energy bar chart, just like we talked about after the icy hot lab, remember these things all happen in stages. Nothing ever happens simultaneously. We're either changing the temperature of the sample of matter or we are changing the state of matter. So for our first practice here, these questions are all going to be looking at just a single change that's taking place. We're either changing the temperature or we're changing the phase of matter. So for worksheet 3, we're going to look at questions 1, 2, and 3. And then your assignment's going to be to work on the rest of the questions from the assignment. So here we go. For each of the problems, sketch a warming or cooling curve to help you decide which equations to use to solve the problem. Keep a reasonable number of sig figs in your answers. So at the top of your paper here, you'll see that we have all of the constants that we've been talking about. The heat of fusion for water. So the amount of energy it takes to either melt or freeze water is 334 joules per gram. That's the heat of fusion. To vaporize water, Or to condense water, we either have to add or remove 2,260 joules per gram. Again, it takes a lot more energy to completely overcome all the attractions between particles. The heat capacity. So again, this is for just warming or cooling a solid or a liquid. To warm or cool solid water, i.e. ice, takes 2.1 joules per gram degree Celsius. But to warm or cool liquid water, it takes 4.18 joules per gram degree Celsius. Again, very different values there. Okay, let's look at question 1 together. A cup of coffee, 140 grams, cools from 75 degrees Celsius down to comfortable room temperature of 20 degrees Celsius. How much energy does it release to the surroundings? So let's start with our cooling curve, our heating curve over here. So I've got graph axes drawn up. I've got T for temperature, and then I've got E with a little arrow. And so let's take a look at what we've got here. It says we're starting at 75 degrees Celsius. And by the time this coffee is done cooling down, it's going to be down to 20 degrees Celsius. So we're starting here and we're ending up here. And so if we draw a line between those two, there's our little graph. Now, my energy here has to be being removed from the coffee. And I know that it has to be being removed from the coffee, energy decrease, because I'm going from a high temperature to a low temperature. So my particles are going to be slowing down. My thermal energy of the cup of coffee must be decreasing as well. So when I look at my equations, I've got my heat capacity, which deals with a single state of matter and its temperature change, or I have my equation for heat of fusion or heat of vaporization, which deals with changing states of matter. Well, coffee is basically 98%, 99% water, and what I have here is water that's cooling down. So that tells me then that I want that first equation, mass times heat capacity times the change in temperature. So, how much energy does it release? That tells me that I am ultimately looking to solve for Q, the amount of energy. As far as mass goes, it says I have 140 grams. Since I'm dealing with liquid here, liquid water, I need to know the heat capacity for liquid water, which according to my constants up here is 4.18. So 4.18 joules over gram degrees C times my change in temperature. Now here's where I got to be careful because it's final minus initial. According to my graph, the final temperature that I'm going to get to is 20 degrees Celsius. And my initial temperature is 75. So at this point, I just need to solve for Q. So I've got 140 times 4.18 times 20 minus 75. First thing I should probably do is figure out my difference here. 20 minus 75 is going to be negative 55. So that introduces a negative sign into my calculation, which is good because I'm removing energy from this cup of coffee. So the change in energy, the heating, my Q value needs to be negative. And it needs to be negative to two significant figures, which if you multiply all that out to two sig figs, we get negative 32,000 joules, capital J for joules, which is our unit of energy. So that's how much energy has to be removed from a cup of hot coffee as it goes down to room temperature. Question number 2. Suppose during volleyball practice you lose 2 pounds of water due to sweating. If all this water evaporated, how much energy did the water absorb from your body? Express your answer in kilojoules. So we've got a few things going on here. First, let's talk about our heating slash cooling curve. I've got liquid water that is being evaporated. So when you sweat, you end up with liquid water on the surface of your body. Your heat from your body then gets absorbed into the sweat, and the sweat turns into vapor that goes out into the air around you. So that tells me then that I've got liquid that is vaporizing. And so I have a state of matter change. And since I'm vaporizing, that means I must be adding energy to the sweat to make it evaporate. Okay, so if I go back to my equations, I'm going to be looking at a phase change. And so Q equals mass times heat of vaporization in this instance, because we're vaporizing this liquid water. So this is a phase change. This is the equation I want. I'm using HV instead of HF because I'm vaporizing this liquid water. Okay, well, a couple other things that are going on here. We're given a mass of water in pounds, which isn't even a mass. So we got to change that pounds into mass, and then we need to get our final answer in kilojoules. So first things first, 2 pounds into grams. And I need it to be in grams because my heat of vaporization is 2,260 joules per gram. So to do that conversion, 2 pounds, the problem here tells me that 1 kilogram is equal to 2.2 pounds. And then I need to change kilograms into grams. And if I do all of that, I should end up with 909 grams of sweat. Now I can put that in for my mass and I can solve my problem here. So Q equals 909 grams times my heat of vaporization, 2,260 joules per gram. And my final answer to 3 significant figures is going to come out to 2,050,000 joules. And in this case, Q is positive because that's how much energy got added to the sweat on the volleyball player's skin to evaporate all that sweat into the air around us. And then our last question here, question 3. Suppose that during the icy hot lab that 65 kilojoules of energy were transferred to 450 grams of water at 20 degrees Celsius. What would have been the final temperature of the water? Okay. Well, we are taking some liquid water here and we are going to be heating it up, but it doesn't tell us what the final temperature is. So that's kind of an interesting situation here on this question. I do know that this water is starting out at 20 degrees Celsius and the temperature is going to be going up to some temperature that I don't know. And that's what the question is asking us. What is that final temperature that it's going to get to? Well, going back to our 2 equations, again, are we dealing with a phase change here, or are we just changing the temperature of a single state of matter? Well, it's the latter. We've got liquid water here that we're heating up, and so we're going to want to go with our heat capacity equation. Q equals mass times heat capacity times the change in temperature. So we've got that. Okay, well, in this equation, we know how much energy we're transferring because we're told that's 65 kilojoules. We're told the mass of water is 450 grams. The heat capacity is a constant. And we know what the initial temperature was. So at this point, we just need to put everything in and then do the algebra to solve for the final temperature. Now, before we get there, we do have one conversion that we need to do. because the energy given to us is 65 kilojoules. Since the heat capacity has units of joules over gram degrees C, we've got to change this from kilojoules into joules. Well, a kilo is 1,000 of something, so 1,000 joules over 1 kilojoule means that we're actually looking at 65,000 joules of energy that's being added in. So that's going to be our Q, 65,000. The mass, we're told, is 450 grams. The heat capacity for liquid water is 4.18 joules grams degrees Celsius times a final temperature, which we don't know, minus our initial temperature, which is 20. Okay. So the first step here, I like to simplify things. So that's what I'm going to start off by doing. So I've got 65,000 on this side. And then if I take 450 times 4.18 and multiply that out. Let's see here, let me grab my calculator quick. 450 times 4.18 to 2 sig figs, that's going to be 1900. Temperature final minus 20. So we got that now. Now I'm going to divide both sides by 1900. So 65,000 divided by 1900. That gives me 34, the 2 sig figs. 34 equals temperature final minus 20. Well, now to get the temperature final by itself, I'm going to add 20 to both sides. And so that tells me then that my final temperature is 54 degrees Celsius. So in these style of questions, we might be looking for the total energy added or removed, or if we know how much energy is being added or removed, we might be looking for something like, in this question, the final temperature. So there you go. At the end of the day, when we're solving for quantities of energy, we have to identify, are we looking at warming or cooling the temperature of a single state of matter, like we did in questions 1 and 3 here, or are we looking at energy changes for the phase change, switching from solid to liquid, vice versa, or liquid to gas, or vice versa. Once we've identified that, which is why we do our heating curve here first, then we know what equation to select. We can look at what values we know, what are our constants, plug those things in, and solve. So that's it. Your assignment for tomorrow is to finish the remaining 4 questions on the reverse of worksheet 3, and then we'll be talking about those tomorrow. So the rest of the time is yours. Work on those to the best of your ability, and then we will go over them tomorrow.